Computer Science 461, Software Evolution. So let's start by taking a look at software evolution. And basically, software development doesn't stop when the system is delivered. A lot of times after the system is delivered, you have new requirements, change requirements, business changes, correction of errors and bugs, new modules that you add in if you're making a video game. And the majority of the software budget in large companies is actually devoted to maintaining existing systems. So what is this system maintenance? Well, according to Sommerville, it's when the transition from development to evolution is not seamless. The process of changing the software after delivery is called system maintenance. I would say that maintenance is what occurs after software is put into production. Now there's other definitions. Your old pal Wikipedia says software maintenance and software engineering is the modification of software product after delivery to correct faults to improve performance or other attributes. And an article from Stratcher and Collier Brown from the 2009 from the Communications of the ACM says software maintenance is not like hardware maintenance. Hardware maintenance is the return of the item to its original state. Software maintenance involves moving the item away from its original state. It encompasses all activities associated with the process of changing software. That includes everything associated with bug fixes, functional and performance enhancements, providing backward compatibility, updating algorithms, covering up hardware errors, creating user interface access methods, and other cosmetic changes. So, how does software evolve and change after it's put into operation? This is part of a study called Program Evolution Dynamics, which is the study of system change. And a lot of this research was carried out by Lehman and Belady, and they actually carried it out from over a period of 30 years from the 1970s to the 2000s. And these resulted in Lehman's laws. Let's take a look at these laws. Law number 1, change is inevitable. Second law, as the system is changed, its structure is degraded. And the corollary to that, one of Murphy's laws, is if you toy or tinker with something long enough, eventually it will break. The third law is a little more contentious and says large systems have a dynamic of their own. In particular, size, time between releases, and number of reported errors is invariant between system releases. And the suggests program evolution is independent of management decisions. Now, I take a little bit of umbrage with the second point under the third law, and that's from Sommerville and is a bit suspicious, given the zone figure shows that 65% of maintenance occurs due to the addition of functionality. We can also look to management information systems to see this is not the case. This model that you see before you here is something called Levitt's model. And this in some ways explains why that third law, program evolution is independent of management decisions, is a bit bogus. Levitt contends that changes in any one of these items, the structure of the organization, the people, the technology, or the tasks, impacts all the others. So, for example, a change in organizational structure will impact the tasks that people perform. It will also impact the technology and the people themselves. So a change in technology will impact the other three. And a lot of times with Levitt's model, you see management depicted in the very middle since it controls all the other aspects. So management can change the structure of the organization, which is then responsible for changing the technology that underlies the organization. So I don't think that program evolution is independent of management decisions. Other laws. Fourth law, over a program's lifetime, its rate of development is approximately constant and independent of the resources devoted to the system development. Law 5, over a lifetime of a system, the increment and change is constant. And Law 6, functionality will continually increase to maintain user satisfaction. Law 7, if changes are not made, the quality of the system will appear to be declining. And Law 8 says evolution process needs to be treated as a feedback system. So these laws mean that users become unhappy if you don't maintain your software, and they think the software is degrading even if it's not. Now that we know some of the dynamics related to change in software evolution, let's take a look at software maintenance in a little more detail. Software maintenance is the general process of changing a system after it's been delivered. There are three types of software maintenance. One is corrective maintenance, that's to repair a fault, and it accounts for about 17% of all software maintenance. Adaptive maintenance is to adapt the software to a different environment, for example, a new operating system or new version of the programming language, that's about 18%. And then perfective maintenance is adding or modifying system functionality to make the system better for users, and that makes up about 65%. So, no discussion of this chapter is complete without a word about some of my favorite figures from this graph. And here Sommerville is trying to illustrate a point that spending more time on developing a stable system can cut down on perfective maintenance. But he, in general, with this case study, pulls the figures from his posterior, and basically he has some very mythical figures that he has made up here, and it's not even a real case study and it's not based in anything, but the graph certainly makes it look as though there is some fact there. So software maintenance costs are easily comparable to development costs, though, is the upshot. Basically what you spend on development, you typically spend that and more on maintenance, and precise specification can lower maintenance costs to some extent. Also getting user sign-off can. And the figure on the previous slide attempts to illustrate that by showing that the system with more development costs will have fewer maintenance costs, but I have no idea where his data originated. So why are maintenance costs so high? Well, several reasons. One is team stability. So after a project gets completed, people tend to abandon ship and to move on to the next challenge. You also have a shift in the responsibility of who performs maintenance. Even if the system is developed internally, they often outsource the maintenance and staff skills. Maintenance is oftentimes seen as not as glamorous a career as development, so sometimes the staff skills in the maintenance department are a bit lacking, and program age and structure. And a lot of these problems stem from the fact that maintenance is considered a separate activity. In terms of age and structure, large systems do tend to decay. This one's actually taken from one of my research systems, and you can see as the system ages, as it progresses from left to right on the graph, there are a lot more outliers in terms of fix time. You can see that over here on the right you have fixes that take a lot longer than they did earlier in the process. There are still a few outliers, but there are far more outliers in this graph as the system itself aged. So to avoid surprises, try to predict, well, what system changes are likely, what parts of the system are going to be really difficult to maintain, and the overall maintenance costs. You need to understand the relationship between the system and its operating environment, the number and complexity of system interfaces, the number of inherently volatile system requirements, and the business process in which the system is used. So this is figure 9.10 on page 247, and these are the this is the process for maintenance prediction. In practice, it's really difficult to predict system maintenance unless you actually believe the previous point about external factors and management decisions not impacting system maintenance. How many change requests can be expected? How in the heck do you come up with that when a custom system goes into maintenance? Again, probably the best thing that you can do here is estimation by analogy. It may be the only thing that actually works. If you have some data on the system for a few years, you can certainly base your estimates on past data, but as soon as the system goes into maintenance, I would say that your prediction is not going to be tremendously accurate unless you have something based on analogy with experience with previous systems that were similar. Now, after you actually have the system into maintenance, you can start collecting some process metrics to see how the maintenance process is going. Number of requests for corrective maintenance, average time required for impact analysis, average time taken to implement a change request, and number of outstanding change requests. So, after you have some of those process metrics, you'll also need to have a process. So software evolution processes vary considerably depending on the type of software being maintained. System change proposals are a driver for system evolution in all organizations. and basically you need a process to deal with change control or change requests. The evolution process includes all the fundamental processes as development, but you need to analyze the existing system structure as an additional consideration. So let's explore some visual representations of these software evolution processes. So here's a cycle one. You have your new system. You have change identification process, so what needs to change or what are the users asking for. Those get put into change proposals that are evaluated, and then the system evolves, which results in a new system. So in more detail, you have the change requests. Systems needs to do an impact analysis to determine what the impact of making the change is on the system, how much time it takes for systems to accomplish that particular task, and whether or not it's going to be, in the long run, have a positive cost-benefit ratio. Release planning, it's good to batch changes, then you do your implementation and system release. And in terms of release planning, is it a fault repair, platform adaptation, or system enhancement, and how do you bundle those changes, because it's good to batch them. On the other hand, you also have to deal with urgent system changes when it may not be possible to follow a long protracted process or a disciplined process. So a lot of times you can have urgent changes that are caused by a serious system fault that occurs that has to be repaired in order to allow normal business operations to continue. Changes to the operating environment that have unexpected effects that disrupt normal operation, and unanticipated changes to the business. For example, new competitors, new suppliers, the law can certainly impact that. And so you may not be able to follow the formal change control process that you put forth. Changes take priority over documentation, but even after you make an urgent change, you still have to go back and fix the documentation. Also, the quick fix solution may not be the optimal solution, so it's worthwhile to go back and fully analyze the change as soon as you've made it and return the system to some point of stability to see whether or not there is a better change that's more long-term. So sometimes you have to do some really serious repair to keep a system actually usable at all. And this is especially true for legacy systems. A legacy system is a computer system or application program which continues to be used because the cost of replacing it or redesigning it, and often because of its poor competitiveness and compatibility with modern equivalents. The implications of the system is large, monolithic, and pretty difficult to maintain. But on the other hand, replacing it would cost more than the current maintenance process, or more than management is willing to put into it. So legacy systems are oftentimes really difficult to understand. The original designers and users have often long since retired, and the same with the developers. The code may be optimized for space utilization or performance at the expense of understanding, particularly things that are written in assembly language. So one solution is something called re-engineering, and this is concerned with re-implementing legacy systems to make them more maintainable. And it can involve one or more of the following: redocumenting the system, organizing and restructuring the system, translating it to a new modern language, and modifying and updating the structure of the data. The critical system is that the critical difference between this and new development is that the old system acts as the specification for the new one. And you don't have to pick all these activities in order to make an engineering or re-engineering effort successful. So benefits to re-engineering versus brand new development. One, you have reduced risks, especially because you aren't recreating the specification. The old system and the old specification still exist. There's often reduced cost. Ulrich, for example, looked at a system with an estimated redevelopment cost of $50 million, and it was re-engineered for about $12 million. So here's the re-engineering process, and you can see several activities, such as source code translation, converting it from an old language to a modern one, analyzing and documenting the system based on reverse engineering, particularly if the documentation for the original is not there. Improvement to the program structure. It can be modified to be easier to understand or to maintain. Modularization, grouping related parts of the program together and removing redundancy. And then data reengineering, which is changing the data to reflect program changes. So what are the costs of reengineering? Well, they depend greatly on the work that's being carried out. Factors that can affect reengineering costs are the quality of software under construction, what type of tool support you have available, extent of the data conversion required, and the availability of expert staff. Again, here's another one of Sommerville's case study figures. He doesn't have any figures to support this, and it's his opinion, so take it with a grain of salt. You can see it on figure 9.12 on page 250. Legacy system evolution. What do you do after a legacy system becomes so old that it's a legacy? Well, one, you can scrap it completely. Two, leave the system unchanged and continue with regular maintenance. Re-engineer the system to improve maintainability, or replace all or part of the system with a new system. So one way to determine what to do with it, which one of these four approaches you choose, is to use a portfolio approach. And this is similar to the Boston Consulting Group matrix and portfolio approaches used in management information systems that we saw in CS 460. If it's low quality and low business value, obviously scrap the system. Low quality and high business value, you may want to re-engineer or re-implement the system. High quality, low business value, continue with regular maintenance until it completely degrades, and then scrap it. High quality, high business value, keep normal maintenance operations. Now, so how do you determine its business value? Well, 4 questions that you might want to ask. How much is the system being used? If it's not being used at all, it has low business value. If it's being used every day, it has pretty high business value. What business processes does it support? Can it adapt to changing business processes and their requirements? Is the system dependable? If it's not dependable, customers will find workarounds or other ways to go about their daily tasks to accomplish the core business. System outputs, what downstream systems does it feed? And also assess the environment and technical quality, which we're going to look at in the next 2 slides. So, for an environment assessment, this includes all the hardware, associated support software, and maintenance processes. So you may want to look at supplier stability, failure rate, age, performance of the overall system, support requirements, maintenance costs, and interoperability. Can this thing actually talk to other systems? Technical quality, you need to assess factors related to system dependability, difficulties in maintaining the system, and system documentation. How understandable is the system? Does it have documentation? Is there a data model? Is data duplicated? What's the performance? What programming language does it use? Configuration management strategy? Do you have test data to carry out regression tests? And what are your personnel skills in that particular area? You can also get quantitative data for assessing technical quality. So some of these are the number of change requests, number of user interfaces, how many forms does the system have, particularly for database systems, and the volume of data used by the system. This is another point of contention. Sommerville contends that collecting this is expensive, but you should probably be doing this type of thing from the beginning. But if you haven't, then I would agree with Sommerville that it is something that is probably expensive to assess. So that'll wrap it up for a little talk on software evolution.